You ready? All right, we're going to get started. So this is, we'll be looking at digital signatures, and to start us off, we'll be talking about aggregating Falcon signatures with Labrador. And to give the talk will be Marius Ardal and Sebastian Colby.
Thank you for the introduction. Yeah, so Marius and I will be presenting this work, aggregating Falcon signatures with Labrador, and this is also joint work with Diego, Katerina, and Akira. So the clicker stopped. Oh, there we go. Okay. So the problem we're interested in is aggregate signatures. So we're in a setting where we have a bunch of signers who want to sign various different messages and send them to a verifier. And in some settings, we might be bandwidth constrained, so sending all of the signatures might be quite costly. So aggregate signatures resolve this problem by allowing to collect these signatures together and combine them in some public procedure, such that we can send one single digital object, which ideally should be smaller than just concatenating the signatures, to the verifier for verification. Now, we've had nice solutions to this problem since the early 2000s. So why are we interested in this now? And the answer is, as usual, the threat of post-quantum adversaries. So these nice constructions we have largely depend on things like pairings, which would be insecure against a sufficiently large quantum adversary. So if we look at the lay of the land in the classical setting, we kind of had everything we could have wanted. BLS signatures are super short, only 48 bytes, and essentially allow aggregation for pretty much no additional overhead. Whereas in the post-quantum setting, if we look at the smallest scheme being standardized by NIST, currently it's at least an order of magnitude larger in just the size of a single signature, and even works that have worked to directly try and aggregate signatures in a sequential model only save roughly 40% over just concatenating signatures. So we'd really like to try and do better than this. So our goal is to construct post-quantum aggregate signatures, and we'd like to be compatible with a NIST finalist for the sake of wide-scale adoption, and we need it to be concretely efficient for all of this to even be interesting. So I mentioned briefly that we have this direct approach that perhaps fell a little bit short of what we could want. So it's worth thinking, like, can we take a step back and maybe take a more generic approach, a more folklore approach, and see how far that gets us? So for this, we'll be needing arguments of knowledge, and here, for some NP relation, we can think of a prover that interacts with a verifier that's trying to convince the verifier that they know a witness for some statement. And at the end, if the verifier is convinced, they can accept, and if not, they can reject. Now, we'll be using this to construct aggregate signatures, which means that we can't really have any interaction with the verifier. So what we actually need is a non-interactive argument of knowledge where the prover sends a single one-shot message to the verifier who's then either convinced or not. And the key property we're interested in here, the way we want to characterize a verifier in some sense, knowing a signature is in terms of something called knowledge soundness. So if a prover convinces a verifier with some probability, then we want there to be an extractor which, given black box rewinding access to the prover, can then produce a witness such that this tuple is in the relation. And the way we characterize this security property is then in terms of knowledge error, which for the purposes of this talk, we can think of as the difference in the probability that the verifier accepts and the probability that extraction succeeds. So how will we use these arguments of knowledge? Essentially, we'll be replacing a signature by a proof that we know some signature which verifies. And then, of course, we can extend this approach to proving that we know many signatures that verify, and then if this proof is short, concretely, or succinct, then we actually have a compressing aggregate signature. So that's kind of the high-level blueprint that we're going to be following in this work. We actually follow this blueprint and achieve concretely efficient aggregation of Falcon and design appropriate constraints for that. And in our paper, we provide sizes and micro benchmarks supporting our instantiation. Then along the way, we encountered some issues with security that we had to address. The first thing was that this folklore approach, there are some very delicate details if your extraction from this argument of knowledge requires rewinding. And that's a gap that we close specifically for hash and sign signatures, which encompasses Falcon. Then we also had the issue that our non-interactive argument of knowledge of choice wasn't actually proven secure in the non-interactive setting. So for this, we devised a new framework called predicate special soundness, which allows us to close this gap. And that's something Marius will be talking a bunch about later on. And using that, we can then prove the Fiat-Shamir transformation of Labrador, which was this argument of knowledge, secure. And it's worth noting that all these security results, sadly, are classical, so that leaves something to be desired. Ideally, we'd like to, or hopefully someone could upgrade these results later on. So our broad template is this idea we need a signature scheme, an argument of knowledge, and we'll combine this to get our aggregate signature scheme. So let's zoom in a little bit on the signature scheme. So here we're using Falcon, and Falcon is a hash and sign signature scheme in the kind of GPV framework, where we sign a message by first hashing it to obtain some element in the range of a function f, and then we use the secret key to compute a pre-image. Verification then entails computing this function forward, which we can do with just the verification key. And as you can see here, I've written out the verification of Falcon, and it has this nice algebraic structure, which will be helpful for our when we prove verification in our argument of knowledge. And of course, we also need to actually check that this element is in the domain, which in the terms of Falcon means that we actually have to check that the signature is also short, which is essential to the security of Falcon. It's worth noting, because of the properties of Falcon, we actually need a salt with, as part of this hash with the message, and that's something that's going to be impacting our security going forward, which we sadly can't really get rid of. So if we look over at the argument of knowledge then, here we use Labrador, which is a lattice-based proof system, and the reason we chose it is that its native language is very well suited to Falcon verification. So there's a nice compatibility here in the algebraic structure can be represented well in terms of constraints for Labrador. And it's worth noting that we actually compute this hash externally to our proof system, and that's because in practical terms, it's inefficient to prove the circuit of this hash function, essentially proving the evaluation of shake. So this is how we choose to use Labrador, and when we combine these, there are a few details about how we instantiate this. So the best setting for Labrador in terms of proof sizes is if you instantiate it with a two-splitting modulus, and you can actually get very nice performant computations if you lift to a composite modulus, because that allows you to use the NTT. And Gregor had a very nice talk earlier this week in his Greyhound talk, where he explained many more of the details surrounding this. So I'd recommend looking at the video from that talk if you're interested. Now, putting all these things together, we actually end up being concretely efficient, concretely competitive with specialized schemes, so schemes that are specifically designed for the purpose of aggregation. So one such scheme is Chipmunk, which operates in a sequential model where for 1,000 signatures here, we actually perform better than Chipmunk in terms of sizes. And here I have the numbers with both with the salt and without the salt. And the reason for that is that we can actually, if we match the sequential model of Chipmunk, where signatures are aggregated for a particular timestamp, then we can actually omit the salt and use the timestamp instead as an input to the random oracle. We can also look at, and if we compare to how just concatenation of Falcon would be in this setting, then concatenation is just under 700 kilobytes. So concretely, for 1,000 signatures, we're saving roughly 82% of the size. And we can look at the trends, how this grows as we add more signatures. And you can see that without the salt, we grow logarithmically, and it's actually concretely a very small additional cost for doubling the number of signatures. And sadly, if we include the salts, we grow linearly, but the savings are still very meaningful because the salt is only 40 bytes out of the almost 700 bytes of a Falcon signature. Now I'm going to hand over to Marius, who'll talk more about the security of Labrador.
Yes, is my mic on? Yeah. All right, so I'll be talking about predicate special soundness, a new framework that we introduced originally to prove that Labrador is a non-interactive argument of knowledge, but it's also a tool that we hope will be useful for others. So originally, Labrador was an interactive protocol, and you make it non-interactive by applying the Fiat-Schmidt transform. So now the verified challenges are obtained by querying the random oracle. And Boylens and Seiler, they proved that the interactive protocol is knowledge sound. And then they heuristically assumed that when you apply the Fiat-Schmidt transform, security is retained. In this work, we want to rigorously analyze the knowledge soundness of Labrador when you apply the Fiat-Schmidt transform. And to explain our approach, I'll need to give you a quick recap on special soundness. So let's look at the three-message case. We say that this protocol is two special sounds if given two transcripts with the same first message but different challenges. We can efficiently compute a W as a witness for a statement. And we can represent these two transcripts as a tree. The nodes are the prover messages, the edges are the challenges, and each path in the tree is a transcript. So this is our two special sound tree. We can generalize special soundness in many ways. First, we can generalize it to K special soundness, where we will be requiring a K fork instead of a 2 fork. You can also generalize it to the multi-round case. Now we have a threshold parameter for each challenge round. So in the first challenge round, you need K1 challenges, and in the second challenge round, you need K2 challenges, and so on. So why do we care about special sound protocols? Well, one thing is that their knowledge soundness is really well understood. So if you look in the interactive setting, then the knowledge error is just the sum for each challenge round of the threshold over the size of the challenge. And then there are these really cool papers that show that when you apply the Fiat-Schmidt transform, the knowledge error only blows up by a factor Q, where Q is the number of random oracle queries that the prover makes. So we're really hoping that can we use special soundness to prove that non-interactive Labrador is knowledge sound. Indeed, the protocol has a certain special sound structure. So it's a commit and prove protocol, where initially the prover commits to its witness and sends the commitment to the verifier. And we observed that if you do a 2 fork at the very last round of the protocol, then these two transcripts allow you to compute a W that's an opening to your commitment. But that's all you can guarantee. You cannot be certain that this W is a witness for your statement. Let's say that we want to try to enforce a stronger property on our W, like that is short. Well, then intuitively, if the protocol is secure, we need to use the challenge round. Like, if you're trying to use a W without this property, then the protocol needs to be set up so that it's hard to answer the challenges in such a way that you get an accepting transcript. So typically, you have a result like this. So if you consider a fixed W without the property, and you sample a uniformly random challenge, then the probability that the verification check will pass is negligible. But we cannot directly use this result in the Fiat-Schmidt setting, simply because the prover can query the random oracle many times to try to find a challenge that it wants to use. And I should also note that we really need to reduce to the binding property of the commitment. If I can, after seeing the challenge, only then pick my W, of course, will not have any security. So the binding property is really important. So I said that I cannot directly use this lemma, but it still tells me something very important. It tells me that a bad W can only use a negligible fraction of the challenges. So our initial idea was, what if I just require the prover to answer to one more than the maximum number of challenges that a bad W failures? Then we know that either the prover was using a W with the property, or at some point, it was using a different W, a different opening to our commitment. Then we have two openings to our commitment, and we have reduced to the binding property of our commitment scheme. That was the initial idea. But then we ran into a problem. So it could very well be that this fraction is negligible, but that does not mean that k is polynomial. It could very well be super polynomial or exponential. In the paper, we devise a different extraction strategy where we only need a two-fork, and using exactly, like we're exploiting exactly how the extractor samples the challenges to actually prove that we also get knowledge soundness in this case. And the kinds of protocols that we can extract, we present in a framework that we call predicate special soundness. So it's an extension of special soundness. So we still use the special sound structure, and we use it specifically to specify how to extract openings. And then, if you want to enforce a stronger property on your opening, you add a predicate. And as long as the fraction that we were talking about earlier is negligible, you'll still be null by sound. So you get this very nice bottom-up approach, where you just start with specifying how to get an opening, and then you add more and more predicates to build stronger and stronger guarantees about W, until finally you can assert that W is a witness for your statement. So we prove that as long as all the predicates have negligible fractions, then the phi-HMU transform of a predicate special sound protocol is knowledge sound. The knowledge error is just, Q times the sum of the fractions, roughly. So when we go back to Labrador, we think, how can we now prove that its phi-HMU transform is secure? Well, that job now just means that we need to prove that it's predicate special sound and that the fractions are negligible.
3 minutes.
Yeah, and then the proof becomes quite modular and simple. I can focus on one property at a time, so the proof becomes very easy to read and then reason about. That's why we hope that this can also be useful for other people that are proving that their multi-round protocol, when you apply the phi-HMU transform, it's still not enough. If you were here earlier on Monday, there was also a talk on statistical special soundness, which is an idea similar to ours. So there's a lot of exciting work going on in this direction, like extensions of special soundness. But that's really all I had to say. So we get predicate special soundness. We get that the building block is actually a non-interactive argument knowledge. We close the folklore gap, so we get a secure aggregation scheme. For that, here's a link to our paper, or the full version of ePrint, and a summary of our contributions. Thank you.
All right, so we have time for some questions.
Thanks. This is a really nice result. Did you prove this also in the QROM?
No, we did not. Yeah, that would be the amazing result if you could lift the results to QROM. But then you would need like some stronger property, right? Because there's a counterexample that multi-round special soundness is not enough to get security QROM. So that would be tricky, but if someone can do it, it would be amazing.
Maybe we could talk after your talk, because I think we did essentially the same. Our talk is on Thursday.
Really? Oh, nice. Okay, definitely, definitely.
Thanks for the great talk. So I guess maybe two questions. First is that this predicate special soundness property seems very cool. And I was wondering if you could maybe somehow relate it to other notions of soundness, such as like state restoration soundness, because I guess in a recent textbook, it was shown that special soundness implied this state restoration soundness, which then implies security of the Eshemer.
I guess in state restoration soundness, I guess it's like a round by round notion? Or?
Yeah. So I was hoping, this predicate maybe could be used as this predicate for the round by round soundness.
Yeah. It's hard to say on the spot. Like, at least one thing is that we slowly build guarantees, right? We kind of depend on what happened in the previous round. So I don't know if that's different from state restoration soundness. I'm not so familiar with that notion, but maybe we could talk after.
Yeah, sounds great. Second question
Sorry,
is...
sorry, I think we're going to have to cut questions off. So yeah, if
Thank you.
want,
We
we
talk
can
after.
afterwards.
Yeah. Thank you.
All right, let's thank the speakers. All right, up next, we have ring signatures for deniable ACHEM, Gandalf's Fellowship, and the speaker is Philip Gayland.
Thank you very much for the introduction. So this is joint work with Jonas Janek and Eike Kids. My name is Philip Gayland, and our paper is entitled Ring Signatures for Deniable ACHEM, Gandalf's Fellowship. There we go. All right, so consider the following scenario. We have a sender on the left and a receiver on the right, and they're assumed to generate their own public keys and secret keys, and they know the other person's public key. And this one-shot primitive involves the sender using his secret key along with the receiver's public key to send a ciphertext over to the receiver. Now, during decapsulation, the receiver would also use the sender's public key. Now, this is the primitive used in the HPKE standard, which was recently standardized by the IETF and is being used in MLS. It sort of finds its roots in the sign encryption literature. But unfortunately, the HPKE standard currently uses pre-quantum primitives. So if we wanted to sort of boost this to the post-quantum setting, what you could do is you could say, okay, use like Kyber to get some notion of confidentiality, and maybe you could use dilithium to get some notion of authenticity. This is great. But the original scheme uses non-interactive key exchanges, so it seems to suggest that there would be some notion of deniability, but this would not give you any deniability. And it would cost you about 3.5 kilobytes in ciphertext. So what we did in this work is basically we show how you can reduce this by 40% to about 2 kilobytes. You still get post-quantum security, and you get deniability for free. So as the title suggests, we did this constructing a new ring signature scheme that is specific for this. All right, let me start with an outline for the talk. So in the first part, I will talk about the ring signature scheme, talk about some applications, I'll show the construction and comparison. And then in the second part of the talk, I will come back to the start of ACHEMs, formalized deniability, something that we considered in this work, and then show the black box construction using the ring signature scheme. All right, so ring signatures, just a quick recap. You have a ring here, a group of users, basically, and they all generate their keys on their own, okay? And a message comes in, and anybody in this ring would issue a signature on this message. And this signature, the two properties that we care about are, of course, unforgeability. So you need, first, a secret key to generate a signature. And second of all, what you care about is anonymity. So given a signature, you should not be able to tell which of these users actually issued the signature. Okay? So that's at a high level what we want from a ring signature scheme. Now, a lot of work has gone into sort of making these efficient, practically efficient. So they're used, they were originally used as a mechanism to protect whistleblowers, but they're also used in like voting systems, digital currencies. I think Dash and Monero are using them. Monero had like quite small rings, I think 11 to users of like 11 users, and now I think it's rings of size 16. But they're also used in theory for sort of notions of deniable authentication. Okay, so I mentioned this, this trade-off about size of rings. So a lot of work has gone into making signatures very small. So asymptotically, the best you can do is you could try and use a proof system. So this is a sort of state-of-the-art construction by Lubashevsky, Nguyen, and Zeiler, where they use proof systems and say, okay, asymptotically, they scale like sublinearly, right? So they scale like logarithmically in the ring size. But this means that even if you have a very small ring, you're always going to start at like 16 kilobyte signatures. So for small rings, it might be better to use like a linear scheme. So here the state of the art would be Raptor. So there the rings, for small rings, you get signatures which are just over 2 kilobytes. And for each additional user that you introduce, you need like something like, I don't know, a couple hundred bytes additionally. But then there is another approach of getting a linear scheme, which is called dual ring, which has better asymptotic behavior, but has larger setup costs. Okay, so these are sort of the trade-offs that we consider. And what we try to do is to see, okay, can we really improve on this small ring size domain? So let me give you an, sort of a warm-up construction about how we go to realize this scheme. So our starting point is really this pre-image sampleable trapdoor function over n-true lattices. So the idea is that you have two polynomials, u and v, that you map to some other polynomial using this function fh. And it is hard to invert this function, so find two u's and v's that are Gaussian distributed unless you have a trapdoor to h, right? So this is sort of from the GPV framework, very similar to like how Falcon works. Now, one way that you could try and construct a ring signature scheme using this function is as follows. You would essentially, for each user, you would sample two small polynomials from some Gaussian, u1 and v1 for user 1, run it through this function, and you do this for all k users, right? And then you would sum up all these terms, and for the party that is issuing the signature at position I, you would use the trapdoor to invert the function so that this sum adds up to the hash of the message and the ring, right? So that's a sort of template for how you would do this. And then the signature would now consist of these k pairs of u1, v1 up to uk, vk. And then you would have to check in the verification, okay, is each pair small, right? Is each ui, vi small for all of the k pairs? Okay, and this is basically how Raptor works. They do like a slightly different abstraction level. They do this via chameleon hash functions, but this is sort of how it works. And in our construction, or our scheme that we call Gandalf, we make some small changes to this template. So how does our construction work? So we still work with these pre-image sampleable trapdoor functions, or n-true lattices, but now the signing procedure will just involve one small polynomial being sampled from a Gaussian, and then you run it, you just multiply it by that person's public key. So h1 is the public key of party 1, u1 is this small polynomial that I sampled, and again, I do this for all the k users in the ring, and what I'm going to do now is that the party that is signing at position I, I'm going to use the trapdoor so party I has a trapdoor to hi, to sample a small ui and v, such that this equation is satisfied. Now, the interesting thing to note here is that my signature now will only consist of k polynomials, right? Not two k polynomials. And interestingly, I do not need to send this v polynomial. Because during the verification, what I can do is I receive all these k polynomials. I just run them through I just multiply them by the public keys. I can do that. I don't need a trapdoor for this. And then what I do is I compute a v such that this equation is satisfied, right? That's what I do during the verification. And then I just check, okay, is this whole norm small? So one thing to note here is that in the previous construction, what I was doing is I was checking the norm of each pair. So that means that sort of security is independent of the number of users. Whereas you'll note here that I will have to set this bound larger if I have more users in the ring, which means that security will actually degrade as I increase the number of users. But it turns out that for the regimes that we're interested in, we can still set parameters that are of interest. Okay, so parameters, how do we compare against the state of the art? So here we have the dual ring scheme that I mentioned, which starts at sort of 4,500 bytes for small rings of size 2. And in the sort of, if you want something even smaller, you can do Raptor, which at sort of rings of size 4 becomes less efficient. So for Gandalf, we basically get a 50% improvement across the board for Raptor. That's because we only need to send one polynomial for each user, not the pair. And we're more efficient than dual ring up to about rings of size 8. Okay? All right, what about the proof? Quick breather. I will not show the proof here, but I will try and show you the security bounds that we get to give you an intuition for the sort of techniques that we use, because I think they're kind of interesting. Okay, so we had unforgeability and anonymity. The notion of unforgeability that we prove is one per message unforgeability under chosen ring attacks. So you can, this is sufficient for the use case that I will show in the second part of the talk. But you can boost this, we show how to boost this like at sort of almost no additional cost to like full unforgeability. So the bound is now upper bounded by some LWE term, which you can safely ignore. The interesting term here is the CISP term, or the ISIS term, okay? So I said that the hardness of this problem would depend on the number of users that you have in the ring. So that's what this beta is going to be here. So beta is the norm bound on this CISP parameter. And the important part here is the kappa, that's the number of users that you have in the ring, and n is the lattice dimension. Interestingly, you get this multiplicative factor c, and this is only going to be a constant. So why is this a constant? So here we use the Renyi divergence to say that the pre-image sampler that we use to actually invert the function to sign, that pre-image sampler is close to a Gaussian. Right? So there we use the Renyi divergence, and we can set very tight parameters. And this is really nice. And the only trouble is that if I now want to prove anonymity, where I can no longer use the Renyi divergence, right? Because Renyi only works for search games. What about decision? So for anonymity, we proved anonymity under full key exposure and multiple challenges. Interestingly here, if you just use like statistical distance with the parameters that we set, you will not get a good bound. You'll get like 2 to the minus 30 or something. So we needed to actually revert back to older techniques using the KL divergence, which you can use for decision type games. And that suffices for the parameters that we set, which is kind of a nice observation. Okay, that's all I wanted to say about the security bounds. And now in the second part, I'll show how we can use this ring signature scheme from the first part to construct an authenticated KEM with these deniability properties. Okay, so just recall the authenticated KEM. We have a sender on the left, receiver on the right, and it's a one-shot primitive where the encapsulation outputs a ciphertext and a key, and the decapsulation also requires the sender's public key. All right. Now, the notions of confidentiality and authenticity are sort of well established in the literature. So the confidentiality notion is sort of inside a CCA, where at a high level, you just say that these shared keys should look random. And then for authenticity, the notion that we considered, and that's been considered in prior works, is the notion of outsider authenticity. But what about deniability? So I said that in the HPKE standard, they use non-interactive key exchanges. So it seems to suggest that there is some notion of deniability there. Well, at a high level, we just want to say the sender can deny having sent a ciphertext. That's what we care about. But let's try and formalize this now. So how would we formalize this? We have a game. We have a challenger on the left, an adversary on the right. And it's an indistinguishability type game where the adversary has to try and guess what bit the game sampled. And he would win if he gets it correct. It's a multi-user notion, so the adversary would get n public keys. And then the adversary can query an oracle, a challenge oracle, specifying a sender and a receiver. Okay. And now, depending on the challenge bit, the game will either output a real encapsulation of the sender and receiver specified by the adversary, or a simulated one. Now, the question is, what do we give the simulator? And also, maybe we can give the adversary some extra information. So that's what we did in this work. We sort of took a fine-grained approach, and we sort of considered all these different notions, right? So we assume we're interested in deniability for honest senders, but what about receivers? We differentiate between honest and dishonest receivers. So what I mean by honest and dishonest, so in the honest case, we just assume that a receiver would not simulate any values. So we don't give the simulator anything. But a dishonest receiver may like simulate stuff. And there the receiver's secret key would be given to the simulator. And then additionally, we consider what keys are leaked to the adversary. So we can either say, okay, the adversary doesn't get anything, or we can leak the sender's secret keys, or we can in fact also leak the receiver's secret key. So we have these 8 different notions that we consider, and it's kind of easy to see that the ones at the bottom right quadrant, they apply the ones at the top left quadrant, but the notion of honest receiver implies that of dishonest receiver for the same quadrant. So say bottom left in honest implies bottom left for dishonest. But interestingly, these notions where the secret key of the receiver leaks in the honest setting turn out to be impossible because they sort of contradict notions of outsider authenticity that we care about. So the strongest ones that one could hope to satisfy are these two here, in the dishonest receiver case and the honest receiver case. So we actually show how we can satisfy both of these notions simultaneously with our black box construction. So our black box construction is going to use the following 4 primitives as building blocks. So we're going to be using a key encapsulation mechanism. We're going to be using a ring signature scheme, the one that I showed you in the first half of the talk. We're also going to require a symmetric encryption scheme and a hash function that doesn't necessarily have to be modeled as a random oracle. We can do it in the plain model. Okay, so how does the construction work? The chem outputs a ciphertext and a key. And what we're going to sign with our ring signature scheme is we're going to sign the chem ciphertext using the sender's secret key. Right? And interestingly here, the ring is going to consist of the public keys of the sender and the receiver. Right? So you do not know if it was the sender or the receiver that issued the signature. Right? That's what you get by this anonymity notion from the signature scheme. And then what you're going to do is we're going to encrypt the signature using the symmetric encryption scheme with the key, with part of the key from the chem. And then we'll output the ciphertext from the chem along with the ciphertext from the symmetric encryption scheme. And then the AChem final key is going to consist of the chem's key and the ciphertext that we get from the chem and encryption scheme. Okay, so this is a construction at a high level. Let me just show you a quick comparison. How do we do? So at the top here, you have the authenticated chem that was presented in the analysis of the HPKE standard. This is not post-quantum secure, but you do really well. You get small ciphertext, you get small public keys. And deniability was not formalized or proven, but we sort of assume, we think that you would get some notion of dishonest receiver deniability there. In the next 2 works from AsiaCrypt last year, you can get deniability at the cost of very large ciphertext and very large public keys in the post-quantum setting. And then this last work was actually presented at Usenix last week in the paper K-Way, and they do really well in terms of ciphertext, but at the additional cost of very large public keys. And confidentiality and authenticity notions are slightly weaker. So in this work, we get the strongest notions of confidentiality and authenticity that are still compatible with both honest receiver and dishonest receiver deniability. And ciphertexts are of size 2 kilobytes and public keys of 1.6 kilobytes. All right, let me wrap up with a summary. So on this final slide, what did we do? We showed an NTRU-based ring signature scheme that we call Gandalf. It's specifically tailored to small rings. So we get a 50% reduction in signature size compared to Raptor. And for rings of only size 2, we have signatures which are about 1,200 bytes. Finally, we formalized deniability for AChem, the primitive used in the hybrid public key encryption standard and messaging layer security. We showed how you could construct an AChem in a black box way, and when instantiated with our ring signature scheme, you get ciphertexts of about 2,000 bytes. Okay. The paper is online under this ePrint link. The QR code will take you to the paper. I'd be happy to take any questions.
Yeah, we have time for a couple questions.
Right. Thanks for the very nice talk and result. I was curious about the distinction I believe in Raptor, where there's like 2K elements and you check the norm of each pair, versus where you have K or K+1 elements. You need to check the norm of the entire thing. Can you say a bit more about the distinction there? Is it some security proof, or could you check UI with V each of these K pairs or something like this?
Okay, so maybe let me just go back to the slide. So in the case of Raptor, you can set parameters such that you only need you can check the couple. Oh, sorry. That's not. Right. Here we go. Right, so in the case of Raptor, you would basically just check these tuples, and then this beta would be independent of the number of users. So the trouble here is that you're going to have to, so the signature will scale a lot, will grow because you have 2 for each users, but you can set the beta smaller. Whereas in the next, in the Gandalf setting, you have to set beta significantly larger to
Yeah, can you say a word about the distinction of why not just use the same beta or use beta for individual K tests?
Okay, so so you're saying why not just check them individually? Mm-hmm. Right. Let me think. So why does this not work? So you would need to, how would you, because maybe we can check offline. Yeah, yeah. Maybe I don't recall off the top of my head, but I think we tried it and we couldn't get it to work.
Fair enough. Thanks.
Yeah.
Okay, we're actually about out of time, so we both can talk offline. Let's thank the speaker.
Okay. Yeah, perfect.
All right, so up next we have polytopes in the Fiat Shamir with a boards paradigm, and we have Hugo Bejnet.
Hello, so I will present you a joint work with Henry, Thomas, Eric, and myself about trying to improve and deepen the understanding of the Fiat Shamir with a board paradigm through the theoretical approach and through the practical approach using polytopes. Oops. Yeah. But before going in, let's just try to get a brief summary of what's already existing for this approach. So there exist 2 main families, the one on the left being on Gaussian distributions. Yet on Gaussian distributions, there are some problems. For the sampling methods are not that efficient, and moreover, in the rejection sampling procedure, there are some underlying problems by using Gaussian distributions linked to the probability density computations. While on the right, there are the uniform distributions. So the 2 that are used in practice are the distribution, the uniform distribution within the hypercube and the one within the hyperbole. These 2 are really nice. First, because usually they are a bit simpler to sample within, while it's not exactly true for the hyperbole. But they have a nice property for the rejection sampling procedure, which is basically, instead of computing the probability density, you can just verify using the computation on the norms. And so, as such, we will focus mostly on uniform distributions for practicality. So, these 2 uniform distributions are linked to 2 signatures. On the left is a signature called 8A that is quite recent, and on the right is the one linked to dilithium. On the left, the signature size is, in a sense, ideal for the Fiat Shamir with the board paradigm, because theoretically, it cannot be done better than that, and we will see why in a moment. And meanwhile, for dilithium, the signature size is, in a sense, for this paradigm, the worst case possible. However, dilithium has a really nice sampler, efficient, simple, and so really enticing for practice. Meanwhile, the ITI one is a bit more complex, and some security properties in the sampler are not verified. And so the question is there a shape or something that embraces the best of the both constructions? And so for this, let's go back on the Fiat-Shamir and the rejection sampling. So the Fiat-Shamir with the board is basically a direct translation of the Fiat-Shamir, basic Fiat-Shamir that you use currently, except that we use lattice-based assumptions. And there is a key difference, which is in the red box, and that is embedded with the abort or the rejection sampling procedure, which basically specifically for uniform distributions is exactly verifying that the Z, the proof of knowledge, is within a certain set to avoid any leakage of the secrets. And so the question is, how can we obtain the shape of Z, theoretically, to improve the efficiency of the signature? So to motivate the rejection sampling, I just want to give a brief example. So the proof of knowledge is equal to Y plus SC, with Y and SC being secrets. So imagine that the set of possible SC is between -2 and 2. The set of possible Y, the set of possible Y is between -4 and 4. And by definition of Z, the set of possible Z is between -6 and 6. Yet, as a signer, imagine that I send Z is equal to 6. Then there is a big problem, because there is only one solution, which is Y is equal to 4 and SC is equal to 2. Normally, in the Fiat-Shamir transform, you need a sigma protocol that ensure the zero knowledge property. And here, without the rejection sampling, then you don't have the zero knowledge property. And the question is how to do that. And to do that, we want Z to reveal no information on Y and SC. And in this particular example, this would be only accepting Z if it's between -2 and 2, otherwise it leaks information. And so here I gave the answer, but overall, how should it be? And here it was in one dimension. So how does it behave in an n-dimensional setting? So to get a good grasp on what the shape of the set of possible Z is, let's take an example here in a two-dimensional example, with a two-dimensional example. So the set of SC is the blue circle, and we take 2 points within it, SC1, SC2. And on these 2 points, we center the orange circle, that is the set of possible Y, like the set where Y lives. And so this orange circle basically defines the possible Z, whether it was built with SC1 or SC2. And so something really nice is that the only area that doesn't leak anything about Z of whether it has been done using SC1 or SC2 is the green area. Yet in SC, there is not, SC has not only 2 values possible. There are a lot of possible values that are within all the values within the blue circle. And so what happens is the generalization of this picture. So this needs to be true for each point of this picture. Yet, now we have quite a characterization for the set of acceptability for Z, but we want it to be the biggest possible, because the bigger it is, the lower the signature size will be at fixed rejection rate. And since we want efficiency, we basically want the set of Z to be the biggest possible. And so we went from trying to get a characterization of the set of accepted Z to a characterization, but that is quite complex in the sense that it's hard to get a good grasp on what's happening in an intersection. And therefore, we propose an answer specifically in the polytope case, for which we work only with polytopes. And with this, we introduce a theorem for which we only work with polytopes and try to get a grasp on what's happening. And to get exactly what's happening, let's take, so for the blue area, a square, and the same for the orange one. So in case SC is within a square, we take a random point within it, and we center the orange square, which is like the set in which Z lives. y lives, and we center the orange square around this point. And we do it for a certain amount of points. And here we see something that is quite interesting, that exactly, remember what we search is the intersection, but there is one shape that remains always within the orange square. And this shape is the inner dashed square that is called BZ, because this is exactly the intersection. So basically what it said is that this intersection on polytopes off-centered within off-centered at each point of a dilation, a smaller dilation of this polytope, preserve the shape, which means that at the end, we obtain the same polytope, which up to a dilation factor, and this dilation factor, we know it. We can compute it. And so the question is, how can we use this for rejection sampling? So now we know exactly the shape in a simple way. I mean, it's no more an intersection. It's a well-defined shape from a well-defined polytope. And so now we can try to work our way through the Fiat-Chami with a board signature. Yet we want something a bit more general. So imagine the case in which we don't take only all the points within the blue square, but only the vertices. Then it happens that we have the same result. The intersection is already the same. And you can ask me, why is it useful? Because in practice, everything, like all the points should be attained. But this is really important because if this blue square has integral vertices, then we can generalize our theorem in the sense that now we can not only work on the polytopes, but work directly on the restriction to the integers of these polytopes. And in cryptography, I mean, we always want to directly work on integral points because it's usually more efficient, easier, and it has some better properties. And so using this, we can directly use, so for example, samplers within integral points, working on integral points, to avoid some problematic thing when we work in the continuous setting. Yet, there is one thing more for practicity. So now instead of taking the blue points on the vertices, let's just take one point on each facet of the polytope. So here on the blue polytope. So here, one point on each facet of the square. And the question is, what's the use? Because we obtain, again, the same result in the sense that the intersection is always the same polytope. It's actually quite useful. Why? Because in practice, the set in which SC lives is actually not the polytope we want to. So SC is the multiplication of a secret S with a challenge C. And in terms of coefficient, it can be seen as a sum of distributions. And by the central limit theorem, it looks like a Gaussian. Then with some slight tweak on the signature scheme, you can make it look like a sphere. And so it's not a square, it's a sphere. Yet there is an important hypothesis that I didn't speak about in the main theorem, is that the polytope needs to admit a perfectly inscribed circle within it, which is perfect because if we take the inscribed circle, it's tangent to each facet of the polytope, at least in one point exactly. And so using this, instead of working directly using all the polytopes under the intersection, we can directly use the hypersphere. And so thanks to that, we can apply directly and practically this transformation to all the Fiat-Chami with the board signatures that use uniform distribution and polytopes, of course. And so now we have introduced a new framework, but the question is, I mean, there is already some studies on dilithium, and the question is, why is it useful? So the goal is to introduce something a bit better compared to dilithium, and to try to go in terms of efficiency to ITA side. And so what do we want? We want a polytope that verifies all the hypotheses of the theorem, of the generalization one, of the generalization two. And we want it to be efficiently sampleable for practicality, for efficiency, and to have a small ratio. So what's a small ratio? A small ratio of polytope is basically the ratio between its circumradius with its inner radius. And it is really useful because the outer radius is basically the proof of knowledge size, while the inner one would be the best possible proof of knowledge size given equal security. And therefore, this ratio is basically the overhead ratio of a polytope. Back to the existing, the existing construction. So the hyperbole has a ratio of 1, obviously, and the hypercube has a ratio of square root of n, which comes from the equivalence between the Euclidean norm and the infinity norm, and which is not ideal. And so to go back on our construction, let's go back on the hypercube. So the hypercube has some strange properties that is not so good, but that will become good. That will become good, sorry. So the radius ratio is square root of n, and there is one interesting point that is its mass is concentrated around the corners, which means that if I take a random point within the hypercube, then with a certain probability, it's, if I take a random point within the hypercube with a certain probability, it's around the corners. And it's even more true as the dimension n grows. And so now if we work with its dual, the cross polytope, that is defined as L1 ball, then we have the opposite because of this duality. So the radius ratio is still square root of n, while the volume is way lower than the hypercube volume. And there is the nice property that the mass is concentrated at the center, which means that if we sample one random point within the cross polytope, then with high probability it will be around the center. And so how do we do something? So the goal is the novel construction is the intersection of these two polytopes to obtain a new one. Why is it so useful? First, by doing this intersection, we reduce the ratio, the radius ratio. And then the other one is that by doing that, we are reducing or removing, all the points that were around the corners of the cross polytope. Yet remember, the mass is concentrated at the center, and therefore, we just remove a negligible volume compared to the overall volume of cross polytope. And it implies two nice things. First, the ratio. The ratio went from square root of n to the fourth root of n. Then, I won't speak about it because of time, but it induces sampling, an efficient sampling method, not as efficient as dilithium, but still efficient in the sense that we use only uniform distribution within intervals and not Gaussian or anything like that. And it doesn't use bimodal, but I will go back to that a bit later. And so in application, cryptographers are greedy creatures in the sense that we always want something a bit more efficient. And so for that, we propose an additional optimization. This optimization comes from the fact that the mass is concentrated at the center. So instead of taking H, the polytope that we defined just previously, we want to take C, that is the previous polytope, intersected with an Euclidean ball of radius theta r, with theta that is equal to 1.5 for cryptographic parameters. So it has a low rejection rate, which means that most of the points from H are within C, which is really important for what I will say in a moment. It's the ratio goes down from the fourth root of n to 1.5, which is really nice in practice. And however, this is not a polytope. So everything that I've presented so far is not useful. Yet it's defined using it's defined by a polytope. And so through a nice, I would say, not tweak, but through a nice observation, everything can work. So instead of directly working on C, you can just apply the rejection sampling methods on H. And so do all the rejection sampling on H, which is a polytope, and on which we can apply all the previous results. And then at the end, when you obtain the proof of knowledge Z, you can just verify that the norm of the Euclidean norm of Z is lower than 1.5 times R. And since there is a low rejection rate with high probability, it's already lower than this bound. And so using this, we obtain some nice results. So in terms of signature sizes, we are in between Eta and dilithium. We're not close enough from Eta because they use something that is the bimodal approach, and that cannot be used on both Patronus and dilithium because of some geometrical behaviors. The verification key is actually smaller than the two of them, and the rejection rate is smaller than the two of them. The result changed a bit because we changed a bit the way to study it using partly the infinity norm instead of the Euclidean norm. But I won't go too deep into details, because it's linked to some part of the signature scheme and the bit cutting that is in it. Note, however, that with the rejection rate, the lower it is, the bigger the signature size will be. And so if you want some, I would say, smaller signature size, by not a large margin, I would say that to gain a bit of size, you can increase the rejection rate to lower a bit the signature. And so, as a recap table, we have a construction that indeed embraces the best of the two worlds. However, it's not like the best of the best. I mean, we don't have the same signature sizes as 8A, and I mean, by far, not by far, but we are not close. And in the same way, our sampling method is not as efficient as dilithium, which is really, really efficient. But still efficient enough and way more efficient than 8A. And so we propose something, however, that in the overall setting is better than these two. And so as a takeaway, so we propose a new framework for Fiat-Shamir with the board signatures using polytopes to do a rigorous analysis on the Fiat-Shamir with the board paradigm. We introduce a novel construction that is defined with the L1 ball and infinity ball to better approach the Euclidean ball. And luckily, this construction allows to sample directly on the integers efficiently, which is a nice property for cryptographic applications, of course. And all this leads to a signature same patronage that is an interesting trade-off between dilithium and 8A. Thank you for listening. If you have any questions, feel free to ask. I will try to answer them, and you can find this paper on ePrint. Thank you.
Thank you. We have some time for questions. So I'll ask one really quickly. Can you sort of talk about, I guess, like real-world applications that might prefer to use Patronus, or like also maybe some like follow-up work that you think is interesting?
So for application, I mean, it would lead to, so we have done an implementation of the sampler in the polytop already directly on the integral points. And it's actually quite efficient, not as dilithium, I mean, in terms of efficiency, but way more efficient than 8A. So I think it's quite practical. And yeah, it just needs like to be implemented. For following work, I would say it's linked to the polytop framework, for which instead of using structured lattice-based assumption, we can use unstructured lattice-based assumption, because using this, we can basically try to construct a polytop that I spoke of, where S times C, in practice for structured lattices, usually looks like a sphere, but for unstructured lattice-based assumption, we can make it look like something different. And using that and some properties on the duality of polytops and intersection, we can try to do something better, and we are working on that, I mean, to try to get like a nice unstructured lattice-based signature.
Great. All right, let's thank the speaker.
Thank you.
Hello?
All right, up next we have Raccoon, a masking friendly signature proving in the probing model. And to present, we have Thomas Frost.
Thank you for the introduction. All right, so the motivation for this talk is as follows. So in 2022, NIST selected 3 schemes for post-quantum signature standards. These 3 schemes were Falcon, Dilithium, and Sphinx Plus. So these are great schemes because they achieve a lot based on several criteria. For example, Dilithium is very easy to implement and can be implemented on a lot of platforms. Falcon is very compact. Sphinx Plus is based on very conservative assumptions, but there is one common drawback that these 3 schemes have, I believe, and I think that some co-authors of these schemes are in the room, and I hope that they agree when I say that they are not very easy to protect against side channel attacks. I'm going to explain why this is the case. And so the motivation for Raccoon was to fill this gap. So when you look at Sphinx plus Dilithium Falcon, when you try to protect them against side channel attacks, you're going to have a quadratic overhead in what is called the masking order. And in the case of Raccoon, we'll only have a quasi-linear overhead in the masking order. Okay, so first let me quickly recall what side channel attacks are. So when you implement your scheme and you deploy it anywhere, so it's not going to work as a black box. It's going to interact with the environment. It's going to leak a lot of information about the data being processed. And this leakage can occur via power consumption, electromagnetic emissions, timing measurements, acoustic emissions, and so on. So, okay, so we have a bunch of ways that this can leak, but we want to find a simple way to model that. So there are two questions that we want to answer for like formalizing the problem before solving it. And there are two steps. So first, we want to find a model that allows us to model the leakage. Second, we want to provide a countermeasure that allows to resist against side channel attacks. And then once we have these two pillars, we want to prove formally that the countermeasure X is going to be secure in the model Z when applied on an algorithm Y. So in this talk, I'm going to take fairly standard and non-controversial models and countermeasures. So the countermeasure is masking, which is the most robust and common countermeasure against side channel attacks. And the idea is that you're going to, so you have a sensitive share, X, you're going to split it in D shares, so you're going to do D out of D secret sharing, such that each of these shares is going to look uniformly random, but when you collapse all these shares and you add them together, you're going to recover the plain text value, the sensitive value. And then computations that are going to be performed using MPC-style techniques. Now for the model, I'm going to consider the threshold probing model, and the idea is as follows, is every time you run your algorithm, to execute your algorithm, the adversary is allowed to see the input and output. Okay, not always the input-output, but the adversary is at least able to probe any t values of their choice inside the algorithm. And this is not a very realistic model because it's not really how it works in real life, but it's a very convenient one because it's very binary. And so for computer scientists, that makes it easy to reason with. And ideally, any set of T probes should leak nothing. And in our case, if we think about masking with D shares and D strictly larger than T, then this shouldn't leak anything. All right, so now let us look at dilithium, and I'm going to explain why dilithium is difficult to mask. So this is a very simple description of dilithium, and so there are 8 steps, and so 2 observations. I'm not going to detail them because they can be explained in other papers. So the first observation is that you need to mask almost all operations. Luckily, we don't need to mask the computation of the challenge, but except for that, we need to mask everything. So for most operations, it's not really problematic because these operations are linear, and linear operations, they are easy to perform in a masked form. But there are 3 operations that are going to be the bottleneck. These operations are step 1, step 3, and step 6 when you do a sampling in a small set, when you do rounding, and when you do rejection sampling. And the current state of the art is that the best way that we know to perform these operations is that we are going to switch between arithmetic masking and Boolean masking. And these mask conversions, they are going to be extremely expensive because their cost is going to be big O of d square log q. In the case of dilithium, q is equal to 23 bits. So even if you mask at order, like with 2 or 4 shares, it's already going to be expensive. But don't take my word for it. Let's look at the numbers. So this is almost state-of-the-art implementation of mass dilithium. It's Coron et al., CHES 2023. So first, if we look at only, so we are going to add mask operation step by step. So in this first slide, I'm only representing the operations that are easy to mask because they are linear, so they can be masked in quasi-linear overhead. And so we can see that it takes less, even with 16 shares, it takes less than 0.01 billions of cycles, so it's less than 0.01 second, basically. But then when you start adding rounding and rejection sampling, then it starts being more complicated. You can see that now you have your overhead become 2 orders of magnitude larger than it was before. And when you add the sampling, it becomes even worse. So we can see that if you want security with a high masking order, when masking dilithium, it's quickly going to become inefficient and you're going to have a problem. So in this case, I illustrated my point for dilithium, but the same point stands for Falcon and Sphinx Plus. And so this motivated us for the NIST competition the new NIST competition of 2023 to propose Raccoon. And I'm going to explain what Raccoon is. So our contribution is as follows. We provide a masking-friendly lattice signature from scratch. And in terms of security proof, we decided to take a flexible approach. So the usual approach that we've seen in other papers is that you have your masked scheme, and you want to show that if you have your masked scheme and T-pros, then this is equivalent to the unmasked scheme. And in the case of Raccoon, we were a bit more flexible. We showed that masked Raccoon with T-probes is harder than unmasked Raccoon with different parameters. And this flexibility allowed the security proof to go through eventually. So in terms of timeline, it's a bit complicated because so first we had a Raccoon at IEEE SNP in 2023, but it was completely heuristic. And then we improved the proposal a lot. We submitted it to the NIST PQC, and this is what I'm going to present in this presentation. Then at Eurocrypt 2024, there was also Plover, which adapted a lot of our ideas to hash and sign. So let me briefly describe Raccoon. So for people who are familiar with lattices, Raccoon is like Lyubashevsky signatures without a board. For people who are not familiar with lattices, then Raccoon is like Schnorr signatures over lattices. So, it follows a commit challenge response flow. And so remember that when I presented dilithium, there were 3 bottlenecks. So the first bottleneck is rejection sampling. In our case, we don't have rejection sampling anymore, so we don't even need to mask it. So the problem disappears, and we will argue via a statistical argument that the secret key is hidden statistically by the noise. The second bottleneck is rounding, and in our case, we can show that rounding is only needed for efficiency, not for security. And in particular, we don't need to mask it. And finally, there is the sampling. And the sampling is the last open question that we need to solve. So let me show you how we solved it. So this is the algorithm on the right is masked Raccoon, the masked signing procedure, which functionally performs almost the same thing as the one on the left. So for sampling, we introduced a gadget which is called adrept noise, which is represented in lime green. And basically in adrept noise, you start with an ephemeral randomness R, which is equal to 0 initially, and then you're going to add a lot of small randomness to it, and you're going to refresh it from time to time. And then at the end, you're going to obtain R, which is the sum of rep times D small randomnesses. And this gadget was formally analyzed in the Plover paper, and in this paper, we showed that T-probing adversary against adrept noise will learn at most T out of these D times rep values. Now there is also the refresh subroutine which is used in this algorithm. So refresh is going to take a masked value and to output a fresh uniform masking of the same value. And it's useful for concrete security. It's also useful for composing gadgets, because if we show that gadgets, they have this property which is called SNI property, and we put SNI refresh between them, then we can compose them together, and then the larger gadget will be SNI as well. And why is the SNI property useful? It's useful because it allows us to move probes around, which will be helpful in the security proof. So now I'm going to present quickly the outline of the security proof. So we start on the left with the T-probing EUF CMA scheme, and then at the very end, we will reduce that to self-target MSIS plus MLWE. So first, we start by making the randomness explicit as input, so this is very simple. Then we use the SNIU property to move all the probes to the add-rep noise randomness. Then once we do that, we use linearity to argue that we can simulate this game 2 from a game 3, and the game 2 is the one where you leak some randomness from your add-rep noise, and the game 3 is the one where you simply take a smaller randomness. And we can show that given the game with the smaller randomness, we can simulate the initial randomness plus some leaked values. And then finally, the final hope is fairly standard. We show the EUF CMA security of Raccoon. We show that this is harder than self-target MSIS and MLWE. So usually this would be somewhat like easy, or at least standard. But because of some design choices we did for Raccoon, it's a bit more complicated, and it required us to introduce the smooth-Renyi divergence. Okay, thanks. All right, so now I'm going to explain what is this issue and how we solve it. So remember that in the final reduction, we argued that when you have the challenge times the secret plus some randomness, then this is statistically close to the randomness. And okay, the question is, how do we choose this randomness? The standard choice would be to pick the distribution chi-R to be discrete Gaussians. And then when you perform the security analysis, you can either perform an analysis based on the statistical distance, which would give you the condition in equation 2, but you can see that there is a factor 2 to the power lambda, which is bad, because it would give you terrible parameters. So instead, we could use the Renyi divergence, which gives us a constraint which is basically proportional on the square root of the number of queries to the signature algorithm. But the downside is that Gaussians are difficult to sample securely against side channel attacks. So while this would theoretically be sufficient, in practice, this would defeat the purpose of, we're trying to build a scheme that is secure against side channel attacks, but if we are using Gaussians, this is defeating the purpose. So instead, we decided to rely on a new type of distribution, which is that we take chi-R, which is uniform over a small subset, and then the sum of all of, and then the final randomness will be the sum of all of that. This is much simpler to sample securely, but then the Renyi divergence proof will go through the window. Why is that the case? So on this slide, I represented sums of uniforms. So you can see the sum of 1 uniform, 2 uniform, 4, and 8, and you can see that it quickly becomes Gaussian-like. But the issue is that the support is finite, and so if you try to compute the Renyi divergence between this distribution and its offset, it's going to be infinite or undefined, so it's not going to be useful. So what we did is we introduced the smooth Renyi divergence, which is a mix between the statistical distance and the usual Renyi divergence. So it's a simple composition between these two. And the way that we defined it allows us to take advantage of the generic properties of F divergences to quickly derive the usual properties that are needed for just doing security proofs. So data processing, probability preservation, tensorization. And so what we did in our proof is that we leveraged the complementary strength of the statistical distance and Renyi divergence, because the statistical distance is very robust. So we use it on the tails where it's problematic to study, and the Renyi divergence gives us very tight proofs, so we use it on most of the distribution. So as a conclusion, we derived a masking-friendly lattice signature in the T-probing model, and while doing it, the design was quite simple, but it required us to introduce new analytic tools such as SNIU or the smooth Renyi divergence. Now I'm interested in open questions. So we did the security proof in the T-probing model. There exist a zillion models for leakage, and we would be interested in seeing the security of Raccoon in these other models, and also to study the concrete resistance. And so if you are interested in our scheme, you can go to raccoonfamily.org. If you are interested in the paper, it's only print, and I'm happy to take questions. Thank you.
All right, we have a couple minutes for questions. I'll ask one really quickly. So I might have missed it, but like in terms of concrete performance, so obviously what you're gaining is sort of like this resilience against probing and side channels, but can you talk about like the performance trade-offs?
In terms of performance, so the nice thing we have is that, so this is the description of dilithium, where we had this some operations were in D square log Q, so the overall complexity when you mask at order D is big O of D log Q. In our case, we only have operations that are linear to perform, except the refresh, which are quasi-linear. So overall, it's going to be quasi-linear complexity in the masking order D.
Also in terms of the signature size or just in the computation?
Oh, right. So the signature size, yeah, this is one of the drawbacks of Raccoon is that because of the security proof, we have a constraint on the modulus Q. So here on this slide, I represented the modulus in logarithmic shape, logarithmic form, and very simplified, the signature size is going to be quadratic in Q. So you want to make Q as small as possible. And so Q is going to be larger than it is for dilithium, for example. So in dilithium, it's 23 bits. In our case, it's 49 bits. And when you look at the signatures, we are indeed 4 times larger than dilithium.
All right, let's thank the speaker.
Thank you.